Hello, my name is Dalton Chichester, and I will be doing a presentation on symbolic methods in synthesized cryptosystems. So hello, and welcome to this talk. The goals of this talk are the following. Give a brief overview of recent and I think interesting work on applying automated reasoning to cryptography, in particular to the automatic generation and security proofs of cryptographic systems, as well as introduce a new tool which is an implementation of some of these methods. This has been a collaboration of a couple of different people, you can see here. First, a very quick look at some background material. In this talk, we will just consider symmetric key block ciphers. It's often useful to talk about these schemes as modes of operation. Most symmetric key ciphers are block ciphers that encrypt only fixed-length plaintext. In order to encrypt plaintext longer than fixed length, the encryptor divides it into a sequence of fixed-length blocks and then encrypts it into a block cipher mode of operation, or MOO. This is a sequence of recursively defined functions on plaintext blocks of fixed length so that each function returns a block of ciphertext. First definition is a mode of operation called ECB. Let E of K be a block cipher with block length n, and let M be the message such that M is equal to a broken up M of M1, M2, etc. Such that M is a set of either 0 or 1 of length n, and then let C be let C of I, where I is either greater than less than or greater than equal to 1 or greater than or less than equal to L, and B n length cipher block such that C equals EK of M, which is just the cipher block equals the encryption of that message. Then the ciphertext C equals the string of all those cipher blocks. Here's a pictorial example of a very simple mode, electronic codebook, it used to be. We have that overarching message being broken up into the smaller messages, and those messages are being fed into the encryption function and then being outputted as a cipher block, and those cipher blocks are being strung together to create the ciphertext. However, given some common notions of security, ECB is not secure. For example, notice that if a plaintext block repeats, then a ciphertext block will also repeat. Thus, an adversary can distinguish when different messages have been encrypted. Here's a more visual example from Wikipedia. You can see the penguin is being encrypted on the right, but we're still able to visualize the penguin even though it's encrypted. So here is a more formal definition of the encryption scheme, but for time we will skip it. It's the same thing. An encryption scheme has indistinguishable encryptions under a chosen plaintext attack, or is CPA secure if, for all probabilistic polynomial time adversaries, there's a negligible function such that defined there. ECB is not CPA secure. Typically, we would develop and then prove CPA security of a MOO by hand, as can be easily done in a negative for ECB. We would like to be able to automatically generate different encryption schemes. However, we don't want to have to prove or disprove CPA security for each of these schemas. We'd like to have the security proof as part of the automated process. Automated reasoning methods have been applied in other areas of cryptography, so we'd like to also apply them here. A method is to start with some set of secure cryptographic primitives, and then to automatically synthesize new cryptographic algorithms out of those primitives. Symbolic methods can be used in several ways in this approach. In particular, they can be used to generate the new algorithms. This typically requires generating algorithms that follow some restrictions. And they can also be used to prove that the new algorithms are secure or insecure, or that they meet some other security conditions. Meadows defines a symbolic condition on MOO programs and their schedules and shows that it is sound and complete with respect to IND CPA security. Essentially, it captures the behavior of a symbolic adversary that is trying to use an encryption oracle to produce a sequence of ciphertext blocks that contain a subsequence that sums to 0 with probability 1. The adversary can only use information that it can compute itself or it has already seen. Thus, it can be considered as attempting to solve a kind of constrained unification problem. IND-CPA is short for indistinguishably from random bits under its adaptive chosen plaintext and IV attack. And here's some more information about it. Adversary is communicating with one of two oracles. An oracle that, given adversarial input P, returns EK of P. And a random bits oracle that, given P, returns a block of random bits the same length as E sub K of P. Number of adversary calls to the oracle is bounded by P of n, where n is the block length in bits and P is the real-life polynomial. After the adversary has finished interacting with the oracle, it outputs either 0 or 1. The advantage of the adversary is either one of these two. Is defined here. Sorry. The first one means the adversary outputs 1 after interacting with block cipher oracle, and the second one means adversary outputs 1 after interacting with random bits oracle. Advantage measures the ability of the adversary to distinguish between encrypted blocks and blocks with random bits. A block cipher is secure if the adversary advantage is bounded by a rapidly decreasing function of n. The goal is to go from a computational representation of the problem to a symbolic one. For example, if in the computational model where all blocks in a MOO problem would be encrypted with the same key, we can model the encryption as here. So a computational model is usually like symbols with hands, and the symbolic one is something easier to be read by a computer, and so that's why we're transferring to that one. For the rest of the talk, we'll be using the symbolic framework developed by Meadows in Meadows 20 to reason about the IND-CPA security models of modes of operation. In this framework, a mode is modeled as a MOO program, which describes the set of all possible symbolic histories of interaction between the adversary and an oracle in the IND-CPA game. The sequence gives in order the plaintext and ciphertext blocks exchanged between the adversary and the encryptor, where the plaintext blocks are represented by free variables. So here we have the same message, but first we have the IV being inputted into the encryption function, also being fed by the first small message, and that gives our first cipher block, which is then also being fed into the next encryption mode, and so on, to get our ciphertext. The MOO program for CBC is a set of possible interleavings of the following form. Let IV be a bound variable representing a random nonce, and then let M be the broken up M's, such that the same thing for some parameter n. Then the very first cipher block will always be IV. And the second one would be the combination of the first message and the previous cipher block. The MOO game for CBC is the adversary starts a new session with the encryption oracle and sends an initial nonce, or IV. Each of the following steps, the adversary sends the plaintext message, P of I, represented by a variable xi. The oracle returns the cipher block I using the function xi xor the previous cipher block. Then the adversary ends the session. When C of I is returned can depend on the schedule, either directly after it is computed or at the end of the session. For simplicity, we will assume it's sent immediately after it's computed by the oracle. Symbolically, we can represent these systems as MOO programs. These can be thought of as a function from a sequence of plaintext blocks to a sequence of ciphertext blocks, together with the schedule for delivering the ciphertext blocks. We can represent these as possible histories which describe the messages exchanged during a process in which an adversary interacts with the oracle to encrypt a message, where the encrypted messages is a sequence of MOO terms. For example, assume you have run the 3 steps of the CBC program, as defined as before. We would then have the following symbolic history. The first is IV, and then it's x1, and then the function of IV, x2 or x1, and so on, x2 in the combination. We move ahead to some of the main results. All the details and proofs can be found in Meadows 20. In Meadows 20, it is shown that assuming the underlying block cipher is itself IND CPA secure, then IND CPA security of a mode of encryption built using only the block cipher F, the exclusive OR operation, and random blocks hold only if certain conditions of the corresponding symbolic MOVE program are met. And we find these below. The restriction to computable substitutions captures the intuition that since the adversary cannot predict the output of F on a given input, or the choice of a random string generated by the encryptor, it can only use such outputs that it has already seen when constructing its substitutions. In Meadows 20, it is shown that a MOVE program is symbolically secure if and only if the corresponding mode of operation is IND CPA secure. In checking IND CPA security, we can think of the adversary as attempting to break a mode of operation. The encryption oracle helps the adversary by responding to encryption requests. A mode of operation is IND CPA secure if the adversary has negligible advantages to distinguish between a sequence of blocks returned by mode of operation and a sequence of randomly generated blocks. The adversary can distinguish between the two sequences if it can instantiate the plaintext in a way that causes two ciphertext blocks to be equal given our equational theory. This is called finding a collision in the literature. However, the adversary can't use any values when attempting to produce equal blocks. It can only instantiate a variable x with a term t if that term has been seen before x in the sequence of the MOVE program. Consider again the ECB example. Notice if we have a symbolic history of x1, f of x1, and then x2, f of x2, it's simple for the adversary to make two blocks equal simply by replacing the variables x1 and x2 by the same term, or plaintext. We get the two cipher blocks are then equal, so f of x1 is equal to f of x2. So the adversary only has control over the plaintext or the variables. However, it can still force a collision simply by finding a substitution on x1 and x2 that makes the cipher blocks terms equal. The following problems are needed in either automating the above process or prove its limitations. Results about decidability of IND CPA security prove in general it's undecidable will show some conditions for which security is decidable, and unification problems needed for automating security, as well as invertibility, a security condition required in cryptographic schemes. The next problem is a new form of the unification problem, which is needed to decide if a MOVE program is secure. In Lynn-Lynch 20, Lynn and Lynch present an algorithm that can be used to answer the following question. Given description of a ciphertext produced by a MOVE, in which a logical variable stands for plaintext, is there any substitution to the variables computable by an adversary so that the resulting ciphertext contains a subsequence that sums to 0? We're going to skip all these for time. So here's an example of an insecure MOVE program based on cipher block chaining. The cipher block chaining with at least 3 cipher blocks is insecure. The cipher blocks F, x1, c1, and fx2, so on, are unfollowable with the x1 is replaced with c1, x2 is replaced with f0. So this is an overview of our tool. We're synthesizing the unification, MOVE programs, symbolic library, and variability checking. One thing that I've been working on is creating an improved multi-equation recurse check. So the adversary does not have an advantage in creating a collision. We can't have a variable defined in itself. So for example, x equals g y, where y equals g of x, z is equal to g of x, and returning back to x. So I'm creating an algorithm that just prevents that happening in our tool. So that is the end of my presentation. Thank you very much for listening. If you have any questions, feel free to email me.